Hello everyone and welcome to day 2 of the Fault2SHA 5th workshop, all hands on promoting faults in seismic hazard assessment. Particularly thank you to everyone who joined us yesterday, whether that was directly on Zoom or through YouTube. We will again today be having our meeting on YouTube and live streaming, and we will also make the videos available to people later on YouTube in case you want to watch again. Please note there will be a couple of interruptions to the YouTube streaming due to permissions for sharing videos. Today, I'm really looking forward to our sessions. We have fault data, processes and hazard modeling examples from around the world. And then later today, we will have examples from South America, which will include a keynote from Carlos Costa on From Neotectonic Faults to SHA in South America, Challenges Ahead. So at this point, I'd like to hand over to the chair of this session and my co-organizer for the meeting, Francesco Vicini.
Thank you, Joanna. I'm really excited to start this new session. I would say that we have many 5-minute talks and a couple of 10-minute talks. So please, speakers, pay attention to the length of your time slot. I will give you a notify you when you're 1 minute left for the 5-minute talk. I'm inviting Marta Gabriela Gomez Vasconcelos for the first talk of the day. And please, Hector Perea, be ready for the next one.
Hi, everyone. Can you hear me?
Yes.
Okay, perfect. Well, many thanks for the invitation to participate in this interesting workshop. I'm Marta Gomez from Morelia, Mexico, and I collaborate in the OLIN project. Today, I'm going to tell you what we're working on in terms of active faults. Next, please. Well, as you may know, the Trans-Mexican Volcanic Belt is a large volcanic arc, which is formed by subduction of the Cocos and Rivera plates beneath the North American plate. Over here, there are a lot of earthquakes. Most of them are subduction earthquakes, but we also have many intracontinental earthquakes. Over here, there's an oblique extension setting, and there are many arc parallel basins. These are tectonic basins in central Mexico, and we're focusing in the central part of this volcanic arc in the Quetzal Lake Basin. And in this basin, the Morelia city is the largest city here. It has nearly 1 million inhabitants, and this city is rapidly growing without nearly any organization. Over here, there are many active faults. We know that these are active faults because we've seen historical earthquakes. As you can see, the red dots. We also have many fault scarps, active sedimentation, and creep movement. And there are at least 23 earthquake sources, could be more, and most of them are unexplored. Just 10 of them have been characterized in detail, the ones in red bold lines. And these faults belong to the Morelia-Cambay fault system, mainly east-west normal faults, but with left lateral component. So there's also northeast and northwest oriented faults that act as soft and hard link structures. So this is a very complex geometry. Next, please. We are working in a database of active faults within the basin and overall the central Mexico. We are characterizing the faults and their seismic hazard potential. Most of them have slip rates between 0.17 and 0.27 millimeters per year, with single section ruptures magnitudes with 6.2 and 7. We want to characterize the rupture, their geometry at depth, and identify multi-fault segments, multi-fault ruptures, and fault segmentation. We hope these studies help for the seismic hazard assessment and in the future for seismic risk and for a better territory planning. Next, please. So how we're doing this? Mainly, we're collecting geological data, which is the first step, to characterize the geometry and kinematics of these faults based on GIS and fieldwork. Some trenches and many outcrops we've studied. We're also doing geophysics campaigns, mainly using magnetometry, seismicity, and electric tomography. And we're also working on a geodetic network in the basin, but we started last year, so the data is not very accurate yet. Next, please. And we're also working on volcanotectonic interactions because this is a volcanic region. We have here the Michoacán, Guanajuato volcanic field. And
sorry, Marta, you have 1 minute left.
Okay, thanks. And we've seen that tectonism here controls the volcanic arc in many ways. For example, it controls the spatial distribution of volcanoes, the morphology, the direction of magma intrusions, controlled by pre-existing faults and by stress field. We've seen that it also controls the magma volumes, and we've seen an interesting relationship between vertical displacement of the faults and magma volumes, and that's why we think there's stress transfer between both of them, and we're exploring more about this. Next, please. And just to take home message, well, there are many future challenges. There's a lot of work to do here and not much people working on these topics. But in Mexico, we're working and we're doing our best towards the seismic hazard assessment and social awareness of active faulting. Many thanks.
Thank you, Marta. I'm inviting the next speaker, Hector Perea, and please, Alba Peiro, get ready your next one.
Hi, thank you, Francesco. So now we are moving from Mexico another time to Europe, to the Alboran Sea, in the westernmost Mediterranean Sea in between the Iberian Peninsula and Africa. Next slide, please. As you know, the Alboran Sea, it's composed by mainly 3 different basins: the Western Alboran Basin, the Eastern and the Southern Alboran Basin. And these basins are more or less bounded by 3 main different fault systems: the Carboneras Fault to the northeast, the Alidrisi Fault to the, let's say, south-center part, and the Alboran Ridge and Yusuf Faults to the center eastern part of the basin. These systems accommodate a large amount of the convergence between Africa and Eurasia. And in addition, this zone is characterized also by low to moderate magnitude earthquakes, but also by large earthquakes that have occurred during historical and instrumental times. Here I will focus on the Yusuf fault, this zone marked with the blue rectangle. Next, please. The Yusuf fault is a right lateral strike slip fault that trends approximately west-northwest, east-southeast. It has a length about 150 kilometers, and it's formed by 2 main fault segments that juxtapose approximately in the center of the fault system, producing this a large pull-apart basin, as you can see here. Also, around the margins of this basin, next please, you can see a lot of landslide scars. And the question that arises here, if these scars are related to the fault occurrence or the earthquake occurrence on the area, or they are different things. Now, I will refer to this blue rectangle just depicted to the northwestern part of this slide. Next, please. In this zone, we acquire in the Sheikh Cruise, we acquire IUV data, high resolution or ultra high resolution IUV data that allows us like less than a meter resolution in the pixels. And also that it's marked the area with this orange rectangle. And also we acquire high resolution, ultra high resolution seismic data, chirp data that corresponds to these dotted lines. Next, please. So here you can see an image from the southeastern part of the high resolution data, where you can see the presence of a large surface scarp. But also to the north, you can see that there is some sigmoidal shapes on the slope of the Yusuf Ridge. And to the south, there is it's not very nice seen here. There are some frontal lobes of landslides. Next slide, please. So moving to the northwest, what we see here is several fault scarps with heights around 0.5 meters that show a distribution quite similar to those observed in recent surface ruptures earthquake, like here in the image corresponding to the Red Christ earthquake. So considering the apparent freshness of these scarps, I wonder if this could be related to some historical surface rupture earthquake. Next, please. Okay, using the high resolution seismic profiles, we carried a paleoseismological study in the area following the Barnes and Ponder approach. And this was done in the northern in one of the northern scarps that we have seen just before.
Hector, sorry, you have 1 minute.
Yeah, okay, I'm close to finish. Next one, please. So here I'm showing you the preliminary results. We are expecting to have some chronological results in the near future. And what we can see, or what we can solve here, it's we have at least 8 events in the approximately 200,000 years. This has been obtained using sedimentary rates. And the last one, the last earthquake, could be related to this surface rupture, so it would be quite recent. Also, from this data, even with all uncertainty related, we have an average return interval about 27.5 thousand years, a vertical displacement that gives us an average of 0.6 meters that could correspond to a slip rate of 0.03 millimeters per year. However, we have to point, I want to point that this is a strike slip fall, so this should be considered as a minimum slip rate. Also, this maximum vertical displacement provides us a 6.9 magnitude, maximum magnitude earthquakes. Next, please. So I'm not going to just read all the conclusions, but I would like to point that in the offshore we have some handicaps to measure lateral displacements. We don't have the preservation of let's say nick points to measure, and we are working on these things. But even though we can just show nice results and with a lot of different information. Next, please. And that's the last one. Thank you so much.
Thank you, Hector. Before moving to the next presentation, I will remember to all the participants to post their question to the chat in the Zoom, and then will be summarized by the moderator in the chat section. Please remember to use @ and the presenter name to indicate if the question is to a specific person. So we can now move to the next speakers, Alba Pena, and please, Felipe Aron, get ready. You are the next one.
Okay, so good afternoon. I'm Alvaro Pena, and I would like to talk about the Rio Grio Pancrudo fault zone as part of my PhD at the University of Zaragoza. Next slide, please. Please, next slide. Wait. We have noticed that there's a master extensional structure in the recent evolution of the Iberian chain, and it is a north-northwest, south-southeast trending normal fault line. It is made of 2 segments. The first one is the Rio Grio Lanzuela, and the second one is the Cucalón Pancrudo fault segments. They are separated by a right relay zone of 2 kilometers wide and totalizing about 88 kilometers in length. This fault is responsible for the sinking of the northern margin of the Calatayud Basin and also controls a number of successive relief elements that are, for example, the Rio Grio Valley in the north of the map, and the Algairen and Sierra Pelarda ranges in the central and southern sectors, among others. Next slide, please. We are now collecting data of recent deformation along this structure, and we have studied, for example, morphological scarps. In the first photo, you can see that these ones are triangular facets along the Rio Grio Valley, or in the second photo, that is the morphological scarp of the Pelarda range. These scarps are gentle, but usually show recent alluvial fans associated to them. Next slide, please. Next slide. Oh, yes. We have also mapped a planation surface of 3.5 million years along the fault trace, which is the one in color red in the map. The difference between the altitudes in one block and the other has allowed us calculating an offset of 240 meters for the Rio Grio Lancela fault segment and around 300 for the Cucalón-Pancrudo fault segment in the surroundings of the Pelarda range. And they result in two slips rates of about 0.07 and 0.10 millimeters per year. Next slide, please. So we have also studied morphological scarps. There is a drainage reversal of the Guaymil River Valley towards the main fault. And this valley originally flew into the Calatayud Basin, resulting in an alluvial system. And nowadays, it is tilted towards the main fault, as you can see in the photograph and in the map. This fact has been evinced by the existence of opposite Villafrancan and Quaternary paleocurrents, represented with red and blue arrows in the map. Next slide. And exposures of superficial ruptures in late Pliocene Quaternary materials have also been studied, normally along the fault trace, like in the first photograph, where the Pleistocene units are offset around 20 meters, but also from a paleoseismological trench recently excavated in Quaternary materials, like in the second picture. So next slide, please. So despite the current lack of absolute ages, there is a clear evidence of Quaternary activity along the fault trace. The probability of a single dip entirely moving is significant, since the relation between both faults may not have width enough to act as a barrier to propagation of the rupture. And the Rio Grio Pancrudo fault zone as a single structure could generate earthquakes of magnitude 7.3 or 7.4. And now if you focus in the map, there are important clusters of earthquakes in the southern sector around Teruel, but these earthquakes are low in magnitude with respect to the northern ones. So the studied area gathers the earthquakes with higher magnitude in the region, and several of them have already been associated to the present stress field that shows an east-northeast, west-southwest minimum horizontal stress. I'm sorry, because this is a mistake in the picture. It would be minimum, not maximum.
Sorry, Alba, you have 1 minute.
Okay. It is under this stress field where the extensional fault system that strikes north, northwest, south, southeast is now moving. So with this framework, I would like to say that the active character and seismogenic potential of the Rio Grio Pancrudo fault zone, which may be the largest macrostructure in the Iberian chain, should be considered in the future evaluation and say of the seismic hazard of the region. So next slide, and thank you.
Thank you, Alba. Thank you for your presentation. I'm inviting Felipe Aron, and please, Ricardo Caputo, be ready for the next talk.
Hello, everyone, and thank you for the invitation to this workshop. The work I'm going to present to you today with my co-authors, Sam, Andreas, Rob, Franz, Jack, Curtis, and George, it's related to a fundamental principle in active tectonics, that the relief, the structural relief, the topography that's been uplifted by faults, in this case, as you can see in this picture, contains information about the behavior, the past behavior of those structures. So what you can see here is the Santa Cruz restraining band of the San Andreas Fault. This is the area of Central California, more or less, for the people familiar with the place. That mountain range you can see in the North American side of the San Andreas system, it's about 50 kilometers long. And then next slide, please. Next slide, please. So the main components of this research, to test this fundamental idea, for that we're going to use the stream power law, which is a geomorphic model of channel incision, which predicts the altitude of every single point in a channel, in a mountain channel, which are function of different variables that can be extracted from a DEM, like the outlet elevation, as you can see there, Z0, the accumulated drainage area, and the channel concavity. Although there are two variables here that you can see in red, which is the uplift rate and the rock erodibility, which are not possible to extract from the public or available information like a DEM. However, next slide, please. The rock erodibility, next slide, please, is okay, however, the rock erodibility, the lithology of the area, so knowing a geologic map of the area, it's a proxy of how difficult for each specific rock is going to be eroded and carved into the specific shape of the river. And then next slide, please. And then knowing the geometry of the faults or the specific variations, as we saw yesterday in the presentations, the alternative model of the geometries of the fault, and using mechanical models, we can obtain a proxy for the uplift rate field. So with that in mind, we're going to show you, next slide, please. What I'm going to show you here is a technique that we use in an inverse fashion. And then we try to solve for the parameters of erodibility and uplift rate to predict what is the channel elevation, minimize that respect to the actual channel elevation, and with that, obtain moment and fault slip rates on the structures responsible of uplifting that relief. So next slide, please. This is the, well, before I move forward, I would like to thank Dave, Paul, and Laurent, and funding from the Chilean, US, NSF, National Science Foundations, and the Research Center for Disaster Risk Management in Chile, please. Next. The study area is located in Central California, as you can see here. That's the San Andreas Fault system with the Santa Cruz restraining band that generates localized compression, as you can see by those black arrows here, and that's accommodated by thrust faults, which are in the North American side of the plate boundary here. And the two main structures there are called Berrocal-Sargent and Shannon-Monte Vista faults. That area has a lot of advantages, as you can see on the list on the right. And next slide, please. But specifically, the Shannon-Monte Vista fault has evidence of quaternary deformation and historic. Next slide, please. And as you can see here from geodetic data solved by you and Paul Siegel in 1996, it is predicted that that structure hosts magnitude 6.5 earthquake, not moment magnitude. And then also the geologists of the USGS have been mapping some of those scarps there and trenches. And as you can see in the picture, there are evidence of quaternary deformation as well.
Sorry, Felipe, you have 1 minute.
Okay, next slide. So, next slide, please. So here are the geologic units that are constrained. Okay, sorry. And then here is the mechanical model to constrain. No, go ahead, please. Next slide. Okay, and then this is the mechanical model that that controls for the uplift rate, knowing the plane motion on the area. Please go to the results. There's 2 slides. Next. And next. So that's the observation channel elevation, then and the area on the top, and then in the middle is the model, and then the residual is down there. And then more appealing for this workshop, go to the next slide, please. We're gonna see an inclined view of those faults here. Next slide. And the slip rates that we obtain are those. Next slide. And then, as you can see, we can solve for the slip rates, which are very fast in this area. And then, as we assume, we can also transform that to moment accrual rates. And then if we assume a slip predictable model, that's and a specific recurrence time, that's as expected magnitude. And then knowing that an earthquake in 1965 occurred right there in that patch, the next one, if it happens, this is 150 years ago, could have the magnitude according to our model that you can see in that table. Thank you very much, and so sorry for rushing.
Thank you, Felipe. Thank you, Felipe, for being perfectly on time. I'm inviting Riccardo Caputo for his talk, and please, Gerard Robert, get ready for the next one.
Hello, good afternoon, everybody. My presence here is not to present data, results, something like this, but just to share with you some concepts, some ideas about how to use faults or in seismic hazard assessment analysis. Now, subduction is explained in the world of subduction, arc-shaped subductions. Next, please. And Mediterranean is full of this kind of subductions, or past subduction becoming collisions and past collision becoming inactive. Anyway, next. I will focus today in the Northern Apennines, starting in Northern Apennines past subduction, which is now a collision, which is still active anyway. Next, please. Okay, this is a simple geometrical shape represented, let's say, the envelope. This light yellow arrow represents what I call a first order geodynamic structure, first order structure. I mean, it represents a shear zone, a major shear zone separating at lithospheric scale, separating two lithospheric blocks, more or less. This kind of structure and formed during, let's say, some tens of million years, and it has commonly a dimension of several hundred kilometers. Within this kind of first order tectonic structures, we could recognize, of course, next please, second order, what I refer to as second order structures, which are major arcs like this, major arcs characterized in plan view by major strike variations, major changes up to and even more than 90 degrees from one side to the other side. They're commonly 100+ kilometers long, and they, of course, based on their geometries, and they are obviously kinematically and in terms of ages, distinct ones, separated. And normally they design, next please, they could design what we refer to as salience and reentrance in correspondence of the reentrance, or their entrance are in correspondence or probably of major crustal scale heterogeneities, crustal scale discontinuities, inherited major structures. And these features, second order features, involve the entire crust, basically involve the entire crust, the lower part of which these features are basically creeping. Also in this case, we start seeing, recognizing an overlap, not only, I mean, a long strike, a distinction, a long strike, but also an overlap in map view. As you can see, they have typical spoon shape geometry, but they are overlap. Next, please. And we could recognize the more external arcs, which are the most active, internal ones, like the Romagna, as you can see, which is less active or even inactive ones. Okay, all these are labeled or could be considered as second order. Nothing to do yet with seismogenesis and seismic hazard in sensu stricto. I'll focus now on one of these arcs, the central one, which is the Ferrara arc, which is probably the most active of all the Northern Apennines. Next, please. Okay, you see the Ferrara arc overlapping in plan view with the Romagna arc on the west, the Emilia, and on the east, southeast, the Adriatic arc. Next, please. Okay, we'll focus on this second order arc. Again, this arc, you can see it is 150 kilometers long. You still have in plan view or long strike, strong lateral variations and a spoon-like shape geometry at depth. Next, within these...
Sorry, Ricardo, you have 1 minute.
Yes, okay. In these, we can recognize third-order structures which still show segment boundaries, strong boundaries. These structures are clearly kinematically independent. They possibly overlap. They are associated with the uppermost crust, mainly metamorphic units and sedimentary cover, which is particularly thick in these geodynamic settings. Heterogeneities, discontinuities, even major crustal faults, which are coeval with the evolution of these. Also, these structures, although these structures are several tens of kilometers long, up to 60, 70 kilometers long, they are could be not considered as seismogenic structures per se, because they are characterized by, next please, by fourth order structures. These are the fourth order structures. The fourth order structure are still have more planar shape geometries, but they are still characterized by angular segment boundaries, gaps, oversteps, something like this. So we still recognize basically hard segment boundaries between each of these fourth order structures. These are the seismogenic structures. These are structures, let's say, starting above the brittle detecton transition, so they are even confined at depth, not only laterally, but at depth. And these are where we should focus on when we analyze seismic hazard. Next, in order to be quick, next. These are the denser bumps you can see of the two 2012 events, May 20 and May 29. 29, yes, next. And these are the two segments, even not total segments, fourth order segments that have been reactivated. I made the exercise next with the last 500 years seismicity with the magnitudes more than 5.4, let's say 5.5, let's say moderate events basically, okay? And you can see the number, let's say about 10 events, 10 segments have been reactivated. These segments on one side constrain the maximum expected magnitude, so we should focus on these in SHA analysis. On the other side, they give us, they allow us to make statistics in terms of recurrence interval, reactivation time of the single structures, but you can count how many of them there are. So you can make some statistics, and this kind of information, this kind of ranking of the structures, I guess, should be useful and should be used for seismic hazard assessment. I presented an example of the Northern Apennines, but I'm sure that you can find other examples, or you can apply the same approach and the same, let's say, philosophy and concepts to other regions of the world. Thank you for the time.
Thank you, Ricardo. Thank you. I'm inviting Gerald Roberts for his talk. After Gerald, we will have questions. We will have 12 minutes for the questions, and then there will be the talk by Tamara King. Okay, please, Gerald.
Earthquake clustering is incredibly important because if earthquakes don't come at regular intervals in time, it's difficult to use recurrence intervals to map seismic hazard. What I'm going to tell you in this talk is that I think that earthquake clustering can be controlled by shear zone interaction. To show you that shear zones are important, the pictures in this slide show you that if you look at the mean elevation in the Italian Apennines and you correlate that with the strain rates derived from measurements of active faults, there is a relationship. On a log-log plot, there's a linear relationship between driving stress and strain rate, and the exponent of that is 3.26. So these diagrams imply that strain rate, which is so important, is proportional to the differential stress raised to the power 3.2. And that's amazing because those are field measurements which agree with lab experiments for dislocation creep happening in the lower crust. So my conclusion from this slide is that shear zone creep controls fault slip rates, and shear zone creep rate is controlled by differential stress. So I asked the question, what happens to differential stress if faults and shear zones interact? Next slide. So this is what happens if shear zones and faults interact. The top left panel is familiar to all of you. This is Coulomb stress transfer. We have a green fault slipping 1 meter. It changes the stress in the surrounding material. But what's less familiar is that you can convert those values into differential stress. So that's the top right panel. So again, 1 meter of slip, it changes the differential stress. By the way, differential stress is sigma 1 minus sigma 3. Also, what's not obvious is that shear zones, when they creep, they also change both the Coulomb stress, the bottom left panel, and the differential stress, the bottom right panel. And the magnitude is large. So for a fault with 1 millimeter per year, sorry, for a shear zone with 1 millimeter per year slip rate, in 1,000 years, you're going to get 1 MPa differential stress change. So that's 10 bars, so it's huge. And what's interesting is that you can see the two equations which link Coulomb stress and differential stress by King et al. Note that sigma 1 minus sigma 3 also occurs in the dislocation creep equation for viscously flowing shear zone rocks. You see it? Sigma 1, sigma 3, it's in two equations. And I would suggest that those two equations have not been linked in the literature in a way to address the idea of clustering. So interaction will change strain rates and slip rates because the differential stress will change in that bottom equation during interaction. So what we need is a field example with some earthquake clusters in it. And we would then use the slip rates in those clusters to model the changes in differential stress and see if we can actually see if this works, because what we need is a test of this hypothesis that I've just advanced. Next slide. So here we have some observations of clustering. These are 6 sites for which we've collected chlorine-36 exposure dating. I'm concentrating on the 2 middle ones, MTV and LEO, Monte Veteri and Leonessa faults. Can you see that when the Monte Veteri fault stopped slipping at about 4,000 years ago, the Leonessa fault accelerated? So the slip is out of phase. And on the right-hand side, you can see there's histories for all those faults. So again, about 4,000 years ago, 5 of the faults accelerated, but 1 fault slowed for 4,000 years. And then it had the 2016 earthquake was a magnitude 6.6. So let's use the slip in these clusters to model the stress. Next slide, please.
Sorry, Gerald, you have 1 minute.
Thank you. The top left slide, sorry, the left-hand panel is the important one. Can you see that the shear zone on the Monte Veteri fault between 15 and 24 kilometers has had almost -2 MPa of differential stress change? Okay, so that is huge because the differential stress in the lower crust is about 10 MPa. That's widely accepted. You may recall the famous Christmas tree diagram with very low stresses in the lower crust. So that will reduce the strain rate by between 50 and 10% of the original value, depending on what number you use. Next slide, please. So you can predict the slip rate changes. That's the red lines. See how it predicts it extremely well. So the calculations predict that when one fault slows, another accelerates, and that matches the observations. But the magnitudes of the slip rate change match the observations from chlorine-36, which I think is an amazing finding. So what this means is that shear zone interaction is a plausible and, more importantly, quantifiable way of explaining earthquake clustering. So thank you.
Thank you, Gerald. Before starting with the question, I will thank all the speakers for the brilliant and perfectly on time presentation. So thank you very much. And Bruno, I read on the chat there are some questions. If you want to summarize some of them, please.
Yeah, yes, sure. I think first of all, we have some answer from Hector to Jan, but maybe it's interesting to have this discussion all together. And the main question is that we have no seismicity on the use of fault. How you can say in some way that it's an active fault? Hector, can you answer?
Yeah, sorry, I was like, I have to
okay, yes,
put the
worry.
mic on. Yeah, what I was just telling to Jan in the chat, it's like, if we are assuming that this is a slow slip deformation or strain zone, so we don't have to expect so much fast slip on these faults. Probably around 1 millimeter, as we saw yesterday in the East Betic shear zone. And that means that we are dealing with a long recurrence time interval for the large earthquakes. So if we have had a recent earthquake, let's say historical or in the last 1,000 years, we are probably at the beginning of this earthquake cycle, so we don't have to expect so much seismicity on the system. That's on one side. On the other side, it's that we are like working on the offshore, so the seismic station coverage, it's not that good. And probably or surely we are losing a lot of small magnitude earthquakes around the area. So we don't have evidence of this microseismicity around the active faults that we can have in the Apennines, in this East-Betic shear zone, or in other places. So maybe the message to take home is like, don't discard some active faults in places where you are not observing earthquake activity at present, at least in these slow deformation areas. That's what I want to say.
Okay, thanks, Hector. And yes, we have a question for Ricardo Caputo. So do you have an idea of which are the slip rates of the first order structure with respect to the rates of the...
Yeah, you listen to me. No, I was writing anyway. First order basically represent most of the first order is associated to creeping in reality, not slip rate, but if you want the shear rate, and it's creeping, and is directly related to the convergence between the two plates. Being a first order, a lithospheric scale feature, it is the rate is associated to the convergence. While and for the second and basically the third order, which are the seismogenic ones, they could be overlapping in plan view, I mean in section view, in cross-section view. So in order, they partition or they take part of the convergence rate in charge of them. Part is still a seismic, occurs at depth, but part of the convergence rate between the two major lithospheric blocks are accommodated by the fourth order structures as slip rates. Slip rates are commonly, for example, the Northern Apennines in the order of fraction of a millimeter per year.
Okay.
Did I answer?
I think so. Thanks. Thanks, Ricardo.
Yes, thank you, Ricardo.
And yes, a question for Gerald. And yeah, they're asking about the discrepancy between your plots are showing a shear zone between 15 and 25 kilometers, and the works in I think literature that show that the shear zone is between 10 and 15, and ask you some comments about that.
Yeah, well, yeah, I'm fully aware of the Alta Tiberina shear zone. I don't think it's very convincing. So there's my short answer. Really, I think the Alta Tiberina shear zone is basically the brittle ductile transition. I mean, there's microseismicity along it, just like in the brittle ductile transition in most parts of the world. So that's my answer to that. Also, read the Cowie paper, which may or may not convince you of the shear zone model I've used.
Okay. Thanks, Gerald. And I think the last one I see is for Felipe. Few comments about your interesting talk, and we are waiting for your paper to have more details, because in 5 minutes it's difficult to have details.
Sorry. Thanks, Bruno.
Yeah.
I understood a little bit the instructions here, and I apologize to everyone for that. So I had, after my conclusions, I have a few slides that I was saving for showing to someone if there were questions about it. Can you show that? It's possible? There is one specifically that goes to the inversion scheme. So which
exactly. If you can answer about.
Yeah, so it's one specific slide, which is after the take-home message, which was the conclusion of the talk. Who has the control of the slides?
Yeah, it's all right.
Go back, please, to the one that's back. No, not that. Yeah, that one. Okay, so this is the integral form of the stream power law, as you can see in the top equation, and so basically the predicted altitude of each specific point in a channel, which is ZP, it's equal to the altitude, the constant of integration, which is Z naught. That's the altitude of the outlet of a channel. And then U over K, many people may be familiar with the KSN value, or KS, the channel steepness. So that's the kernel of integration, yeah? So U and K, U is the uplift, the rock uplift of the mountain range, which we're assuming is due to the activity of the fault over time. And then K is the erodibility, which is basically how easy for each specific rock inside the channel is going to be eroded. And then we assume here that the major proxy to constrain erodibility is the lithology. Okay, so it's more difficult to erode a granite than a sandstone, for example. Well, depending which sandstone, of course. And then A, which is the accumulated area over the river, and theta, which is the exponent of A, that's the concavity, both can be computed from the DEM. So basically for this model to work, you need a DEM, a geologic map, and an architectural or a structural model of the main faults which are responsible of uplifting the relief. And then having those faults and having the discretized shape of the plate boundary, in this case, with a mechanical model, we use boundary elements, we can solve, for example, for the plate motion, which is V here, and that will give us, after you move the numerical sandbox, the faults are going to interact, are going to create uplift, and that uplift, it's dependent on the plane motion, which can be divided in the normal and shear component in this case. And so what we basically do, we solve the minimization here for 23 model parameters, which are in this specific case, 21 geologic units, so 21 Ks, erodibilities, and Vs and Vn, which are the best fit parameters that are going to create a specific uplift that when you lump it into this equation, is going to reproduce the observed topography, as I show you in the slide with the residuals or the topography. So we're matching that quite well, assuming that this is an inversion not of geodetic data, this is an inversion of geologic data. So assuming all the variability, the epistemic uncertainty involved here, we were very satisfied by the specific residuals we found after solving for this model. And then I have other saved slides here that show the comparison of how the parameters of erodibility and plane motion are compared to other published data, and they are spot on what has been published using geodesy, paleoseismology, and other things. So basically the take-home message here is combining those geomorphic and mechanical models are very helpful to estimate slip rates.
Thank you very much. Thank you very much.
Okay, thanks.
Yeah, I know that it's not easy to present a research in 5 minutes as well as do some questions. Anyway, I think we had a lot of very interesting topics for the discussion. We will have on the third day of the workshop, the 2nd of December. Now we can move to the first of the 10 minutes talk by Tamara King. And please, Jack Williams, get ready for the next talks. And Tamara, I will notify you when 3 minutes left.
Well, thank you, everybody. I'm very glad to be here today. So I'm currently based at the University of Oxford as a Comet funded postdoc, but I did my PhD research on Australian faults, and that's what I'm talking about today. So my PhD research was with Mark Quigley and strongly supported by Dan Clark at Geoscience Australia. And some of the questions and lessons in this talk are generally applicable to stable continental regions or interplate regions, which is not everyone here today, but there is some information that might raise some questions about assumptions for seismic hazard assessments elsewhere. So can I have the next slide, please? Next slide. Yeah, cool. So I'm going to give you a very brief overview of the seismic tectonics of Australia because most people aren't familiar. Sorry if this is a little bit overwhelming. So on the left-hand side, you can see seismicity in Australia. We have 4 regions of higher seismicity. 3 of them are co-located with our largest capital cities in Perth, Adelaide, Melbourne, Sydney, and Canberra, in those white boxes there. We've had 8 onshore magnitude 6 or above earthquakes since 1941. So that's quite high relative to our tectonic location, you know, in an intraplate stable continental region. And importantly, all of those big earthquakes in the red there, those magnitude 6 or above, have occurred in the center and west of the continent. And we wouldn't have known that those were likely. There was no prior seismicity. There was no suggestion that they were going to happen. They were very out of the blue. On average, we have 2 magnitude 5 or above earthquakes a year, which is kind of low relative to global standards, but it's kind of high for Australia, right, or an intraplate area. Importantly, that sounds like a low magnitude, but in Australia, seismic waves attenuate very differently, so seismic shaking is quite high in our crust. So those lower magnitude earthquakes can be quite damaging and fatal, as we saw in the magnitude 5.4 Newcastle earthquake, which killed 13 people. In the right-hand side of the figure, you'll see that we have over 300 potentially active or known active faults. Those are the red lines. And those are well aligned or aligned with the current crustal stress field in Australia as identified through borehole breakout. So that's the direction of maximum compressive stress in the continent. And that changes, the direction of that changes across the continent because far-field boundary forces are having a big impact on the stress field in Australia. So the Himalaya, Papua New Guinea, Indonesia, New Zealand, subduction zones and collisional zones change the direction of compressive stress in the continent. I think that's all I want to say there. So next slide. So in Australia, we've had 11 historic surface rupturing earthquakes in 52 years, which is an incredibly high number, again, for an intraplate stable continental region. Those magnitude ranges are 4.7 to 6.6, so we have a lot of earthquakes. I think there are about 4 surface ruptures less than magnitude 5.5, which is uncommon on a global standard, but for Australia, again, it's relatively normal. These earthquakes are very shallow, so we think that they're all less than 7 kilometers depth. Probably more likely less than 3 kilometers depth. And when you have such a shallow earthquake, the fault plane itself intersects with the surface, or it's more likely to, so you get a surface rupture. On the left-hand side, you see all 11 surface ruptures to scale with each other. So the largest was the Meckering earthquake, which is 37 kilometers long, down to the Pukacha, which is only 1.5 kilometers long. And in the center map there, all of those yellow stars show you that all the surface ruptures occurred in the center and west part of the continent. Something that I forgot to say on the last slide is that the center and west part of the continent, that middle gray area, is the oldest part of the continent. It's this pre-Cambrian crust. It's very, very old, and it has bedrock very close to the surface. The eastern part of the continent is younger, and so we see a lot more topography being built over active faults in the eastern part of the continent. But in the center and west, in that pre-Cambrian part of the continent, the active faults seem to be working differently, which is what I'm talking about today. The right-hand slide there shows you that we build this case in Australia that all of the surface ruptures historically have occurred on pre-existing bedrock structures. So that's pre-Cambrian faults, foliation planes, dike intrusions, any planar feature that might act as a fault. If it's well aligned with SH max, the direction of maximum compressive stress, those bedrock structures seem to be capable of hosting moderate magnitude earthquakes and rupturing to the surface. So in the case of Marriott Creek and Peterman there, those earthquakes were hosted on pre-existing bedrock structures, and we build that case for every single surface rupture. And those occur in single or multi-fault ruptures. I'll go to the next slide, please. So what we want to know for seismic hazard is not only where the active faults are, but the recurrence and the slip rates, right? That's such a key thing that we've all been talking about. It's very hard to get to that with these surface ruptures in Australia. So we took this multi-methods approach for the Peterman earthquake. This was a magnitude 6.1 earthquake in 2016. It ruptured 20 kilometers long in the central deserts of Australia. And the first thing we did was we dug 2 trenches, fairly typical paleoseismic activity or method. And in those trenches, we only find offset of the Quaternary sediments from the modern earthquake. So there's no pre-existing ruptures through this sediment. We date those sediments at 10,000 years. So we know that there's not been an earthquake on that fault since 10,000 years, but we also know that we have to go way back in time in this intraplate context. So in the far right there, you'll see a pre-event DEM that's made from worldview imagery that Ryan Gold and colleagues published a few years ago. And so we analyzed the pre-event DEM and the post-event DEM to try to understand whether there's any pre-existing topography or geomorphic changes. So drainage patterns or whatever, to suggest that there might have been a rupture on this fault previously. And we see absolutely no evidence. There's no evidence of any scarps in this landscape or any geomorphic changes. So we know that before 2016, if there was an earthquake on this fault, it's been completely removed from the landscape. So then the last thing we did is some sampling of granite outcrops across the rupture. So that's very close to the rupture, within about 10 kilometers, and also at far distances, about 50 kilometers. So we sample the granite, we get the erosion rates from beryllium-10, and then we wanted to test whether this hypothesis that erosion rates close to the surface structure might be higher than further away because you've offset the hanging wall, the bedrock of the hanging wall has gone up, so it might have higher erosion rates, or you've shaken the bedrock, so it might have higher erosion rates from that shaking. We find no evidence of any higher erosion rates closer to the surface structure, and we can extrapolate those erosion rates back to 500,000 years because there's no glaciation in Australia. And so it might suggest that up to 500,000 years ago, this erosion rate has been the same. But there's a lot of assumptions in that particular one. The last thing we did here is we said, well, there's no existing scarp in the landscape, or at least there wasn't before 2016. So how long would it take to take that scarp out of the landscape? And if we assume the same dimensions as the historic rupture and use our erosion rate data, it would take 500,000 to 1 million years to completely remove a similar scarp from the landscape. So that would suggest that we haven't had any earthquakes on this fault for about 1 million years. And so recurrence is either over 1 million years, or there's just been no earthquakes on this fault ever before. Before 2016.
Sorry,
yes?
Tamara, you have 3 minutes.
Thank you. So before 2016, perhaps there was no earthquakes on this scarp. So this wouldn't have been an active fault. We couldn't have mapped it as an active fault. And importantly, we couldn't have derived a slip rate. And we still can't derive a slip rate for this fault, right? So this is an active fault without a slip rate. Next slide, please. Sorry, I can't do that. And so just as an overview, all of the historic surface structures in Australia from available paleoseismic evidence, we cannot derive slip rates. There's no evidence that any of these faults have ever hosted earthquakes before. So it's a similar sort of thing. We can't map them as active before they hosted moderate to damaging earthquakes, and we can't get a slip rate from them. Next slide, please. But that's not the case for all faults in the Precambrian crust in Australia. There is some evidence of trenching across paleoseismic scarps to suggest that some of these faults can host recurrent earthquakes just over very long time periods, 10 to 100,000 years or more. Next slide, please. And when we looked at the east of the continent, so in that younger crust, we do see faults that host recurrent earthquakes. So the Lake George fault on the left there is right next to Parliament House. It's hosted 250 meters of uplift. And on the right there, you see the Cadell fault, which has offset the Murray River a few times. And so we know that these faults are active, they're building topography. But when colleagues like Dan Clark have gone and measured that uplift, the cumulative slip, they've found that these faults seem to be turning on and accumulating slip in short periods of time and then turning off in these long quiescent periods, and then they turn on again. So we don't know if these faults are in active periods or quiescent periods, which is a real issue for seismic hazard modeling. Next slide, please. So we have this problem in Australia that we have a very short seismic record. We have the biggest earthquakes occurring away from the most active faults, which doesn't make much sense or is kind of unusual or annoying. And we also have non-homogeneous fault activity. So in the older part of Australia, we have faults that might not have prior earthquakes on them, and some that do, but are very long recurrence intervals. And in the east, we have faults that are hosting earthquakes, but they're doing them in these active and non-active periods, which are hard to predict or forecast. Next slide. And so there are seismic hazard maps for Australia. Geoscience Australia has done these, and they're quite difficult to do, but they've done a great job of this in trying to take away the bullseye effect of these historic surface structures. But at the same time, they're still inputting fault inputs with slip rates when we know that some of these faults don't have slip rates. So that's a bit of a problem. We have this non-homogeneous seismic potential. Last slide. And so the questions I want to leave you with is, should we be incorporating fault sources if they don't have slip rates or at all in these sorts of areas, these really low strain rate areas? If we know pre-existing bedrock structures can control the faults, maybe we could just map faults or a seismic risk from geophysical data. And then we still have the unanswered question of how strain is partitioning across the crust and why it's doing it differently in different places. And that's all, but I do have one last slide. So I'm currently working on Central Asian hazard studies with COMET. We're about to release a fault database with slip rates as well. And we also have lots of other data that you might find useful on the website. Thank you very much. I think that's all.
Thank you, Tamara. Thank you for a very interesting talk. And so I'm inviting Jack Williams. Jack, you have 10 minutes, so we'll notify you 3 minutes left. And please, Ame, get ready because you're the next one.
Okay, good afternoon, everyone, and thank you for sticking around for my talk. So today I'm going to be presenting some results of the PREPARE project. So this is a collaboration between earth scientists and earthquake engineers at Cardiff and Bristol University, and also very importantly, working with colleagues in Malawi as well. So in particular, working with the Geological Survey there and the University of Malawi. So next slide, please. So I think it's quite clear that when you consider the three components of risk, hazard, exposure, and vulnerability, that seismic risk in East African Rift is increasing very fast. You've got very fast population growth, increasing exposure, and you've got a proliferation there of seismically vulnerable building stock. So, even quite a moderate sized earthquake there has the potential to cause a lot of loss. So it's really important that we constrain the hazard component of seismic risk well. So next slide, please. So when we consider previous seismic hazard assessment in the East African Rift, it's mainly considering just the instrumental record of the earthquake. That's the figure you can see there on the left. But when we consider the fact that that instrumental record is quite short, the rift itself is extending quite slowly, and the faults there seem to be quite long and likely to be locked, so they probably host quite infrequent large earthquakes, then it's likely that instrumental record might not be, telling us everything. Like, hopefully I don't need to convince the Fault2SHA community that including faults in seismic hazard is important, right? So some of these points were considered in a study by Hodge et al. 2015, where they did a seismic hazard assessment for Malawi, just using some kind of simple fault and geodetic data. So the diagram on the left there is showing a PSHA map with just using the instrumental record. And the one on the right is showing that actually if you include faults, you can change your maps quite a lot. So if you just click on again. So I think there's a really strong need for us to be developing some fault sources for PSHA in the East African Rift. But there's reasons why this hasn't been done before, right? The active fault mapping there is pretty incomplete. And there's pretty much no paleoseismic trenches or kind of on-fault slip rate measurements across the entire rift. So next slide, please. So we've mainly been working in southern Malawi. So this is kind of at the kind of southern amagmatic end of the East African Rift, south of Lake Malawi, where the rift is onshore. And kind of the first thing we were trying to do is just actually systematically map the active faults, which we did using a combination of high-resolution digital elevation models, some geophysical data sets, old geological maps, and 2 field campaigns in 2018 and 2019. And we're kind of making the assumption in this database that any fault that kind of shows activity during the current East African phase of rifting, which is in this part of the rift is about mid-Pliocene in age, is still active. And we've compiled this all into what we call the South Malawi Active Fault Database. And similar to some of the databases we were hearing about yesterday, this is very much a kind of objective fault mapping databases, just the kind of geolocation of the fault traces and some kind of confidence levels on whether these faults are active and the quality of the mapping. Next slide, please. We've also created a complementary database, the South Malawi Seismogenic database, where we've actually been able to derive some kind of slip rates for these faults using basically by assuming that in an amagmatic continental rift, most of the strain should be kind of on the edge of the rift, on its kind of bounding faults, and the intrabasinal fault should be quite low slip rate. And we've combined that with some earthquake scaling relationships to get an idea of their earthquake magnitudes and fault recurrence intervals. I'm not going to go into full detail on this work. If you're interested, there's a reference listed at the bottom of the slide there of this work, which is currently in open review in Solid Earth. But kind of the headline values essentially are that in southern Malawi, there's evidence that these faults are capable of hosting magnitude 6.5 to 7.8 earthquakes about every 10 to about every 1,000 to 10,000 years, but with some quite large uncertainty on that. Next slide, please. So next, I'm going to focus now on how we actually input this database into PSHA. And the way we went about doing this was to generate these 1 million year long event stochastic catalogs, where the recurrence intervals of faults follow a Poisson distribution, where the rate parameter is the intermediate recurrence interval estimate from the seismogenic source database. And I should also mention that the faults in southern Malawi, they tend to be kind of segmented. And so we've kind of, considering cases where they may rupture and use kind of small individual discrete sections, which are typically bound by fault geometry, or they rupture along their entire length. And we've given that in our synthetic catalogs, we've given that a 50-50 weighting of which of those occurs. So you can see on the top plot there, this is showing the distribution of recurrence intervals for one fault system, the Zomba fault. So the thick black line is showing that it'll have quite infrequent recurrence intervals of around about 1,000 to 2,000 years, but more frequent individual section ruptures about every 500 years or so. We've also generated a comparable background using the aerial source zones that have previously been defined for the East African Rift, which is also 1 million years long. And the correction we've made for this from what's been done before is that we're not allowing any earthquake greater than magnitude 7 in southern Malawi in the area where we've been mapping these faults. And you can see there on the bottom plot the magnitude frequency diagram of these catalogs. So next slide, please. So kind of final part of PSHA, there's pretty much no strong ground motion data that we're aware of in East Africa. So we've been considering some global ground motion prediction equations, but we have incorporated the USGS VS30 map for Malawi, which does quite a good job, even though it's based on topography, of kind of differentiating sites that are on strong metamorphic basement or in kind of weak unconsolidated rift sediments. Finally, for working out the source to site distances, we've gridded the faults, and the width of the faults are estimated from the Leonard scaling relationships between fault length and width. And as you can see, that leads to some quite wide faults in Malawi, but actually that's entirely consistent with the fact it's actually got unusually thick seismogenic crust, about 30 to 35 kilometers.
Sorry, Jack, you have 3 minutes.
3 minutes, cool. I'm just coming up to the results. So next slide, please. So these is some site-specific analysis for Zomba. This is a city on the edge of a rift, about 100,000 people there. And the kind of headline values that our approach has estimated a higher 10% in 50-year PGA compared to what's been done before from the GEM model for Malawi, about 0.18 G. What's really noticeable is that by including the fault sources in our PSHA, if you look at these seismic hazard curves, then you'll notice that at kind of the lower annual probabilities of exceedance, the fault sources are much more important in contributing to the hazard, and also at longer vibration periods as well. So the plot on the right there is the spectral acceleration of 3 seconds. You can see the fault sources are the main source of the hazard. Next slide, please. Again, if we look at disaggregation plots or uniform hazard spectra, we again see that the fault sources really become important at kind of the longer vibration periods and long return periods. So for example, in the disaggregation plots, the one on the left is 10% in 50 years, the one on the right is 2% in 50 years. And we can see that for the 2% in 50 years, magnitude 7 to magnitude 8 earthquakes, the distances up to 100 kilometers away are really become important. So it's again showing that including this fault source information is really important for kind of infrequent large magnitude earthquakes in the East African Rift. Next slide, please. So this is our final slide. So this is our PSHA maps of southern Malawi. They're all for 10% in 50 years. The one on the kind of top right is the GEM, current GEM map for Malawi. Sorry, apologies, this is just a screenshot. But you can see that it's pretty much a uniform hazard across southern Malawi, whereas in our maps, we're, I think, doing a much better job of being able to show how the active faults are actually big contributors to hazard in this region. And just, emphasize, this is a region here of about 8 million people living in, very fast population growth. I think it's very important that this community starts thinking about how we can use faults in PSHA in East Africa more. If you'd like to hear more or know more about our project, then please do email me or go from the usual social media channels. Thank you.
Thank you very much, Jack. Thank you for your interesting presentation. We can move to the next talk by Ruth Hamey. It's a 5-minute talk, so I will notify 1 minute left. And please, Pierre Lancan, be ready. You are the next one.
Thank you. So I'm going to talk today about seismic risk to Almaty. Next slide, please. So Almaty is the largest city in Kazakhstan in Central Asia. And as you can see from the photograph and the Google Earth image at the bottom of this screen, the city extends right up to the mountain range front. There have been a number of large historical earthquakes that occurred in these high mountains, but what we're particularly interested in is identifying if there are smaller splays in the city of Almaty that we might be able to identify. Next slide. And again. So to do this, we're creating high-resolution digital elevation models using optical stereo imagery. So here we have spot imagery, which is 1.5 meter resolution, and you can see it extends across the whole of Almaty city. Next. We also have Pleiades imagery at 0.7 meter resolution, mapping the range front. And next slide. So for each of these areas, we have stereo imagery. This means we have images taken at different angles, and by using photogrammetric methods, we're able to create a digital elevation model across the whole of Almaty city in really high resolution. Next. So to convince you that I mean really high resolution, on the left, we have here free SRTM 90 meter resolution, and on the right, we have the Pleiades DMs that we've made across Almaty. So you can clearly see roads and individual buildings. And it's really these high resolution DMs that we need to tease out small structures and faults within the city. Next. So we've characterized a city that goes through the center of Almaty. This is visible in the field. Next. You can see I've put on here to highlight this change in topography behind the row of parked cars. And this is evidence on parallel roads, suggesting it's extending throughout the city. We've identified this in our high resolution DMs, and at the bottom here in the profile, we fit a line of best fit to the GPS that we took of this fault in the field, suggesting an offset of about 2 meters. In addition to this fault that goes through the center of Almaty, next, we've identified a fault in the north, a fold in the north, sorry. So you can see from the profiles, the elevation, and in this map, the red bulge showing this fold, and we interpret there to be a fault causing this. Next. We use GEM's OpenQuake engine. I think I'm preaching to the converted here to say that it's a brilliant piece of software, and we use scenario mode, which means that we define specific fault geometries and earthquake parameters, and using these defined scenarios, calculate the hazard and risk to Almaty. Next. So for the scenarios that we define, we start with some historical examples. So there were 3 large earthquakes that have occurred in Almaty. Almaty is shown by this black outline, and each of these fault models, red indicates the fault at the surface and blue is the fault at depth. So we've modeled these large historical earthquakes to see what would happen to Almaty if these earthquakes were to have happened today. Next. In addition, we define hypothetical scenarios based on our fault mapping. So this includes the northern splay, where again, red is showing the fault at the surface. This extends under much of Almaty, as well as a fault to the east on mapping from our collaborators, and the fault throughout the center of Almaty, which we identified from our imagery and in the field. Next. So to
you have 1 minute, Ruth.
To jump straight to the results. Here I'm showing you the city districts in Almaty, and the blue colour indicates the number of buildings that show complete damage. So if you click twice, these are the three historical examples. And as you can see, compared to 100 years ago, the population of Almaty has grown significantly. So if any of these events were to have happened today, you're looking at thousands of buildings being completely damaged. If you click to reveal the bottom row, in comparison, we have our hypothetical scenarios. We modeled these as smaller events, so magnitude 6.5 compared to 7 and 8, but because of their proximity to Almaty and the fault extending under much of the city, these are much more damaging. So if you click once more to look at all of the scenarios we have here, you'll see that the northern splay is a significantly larger event because the fault is so close and so much of Almaty is directly on top of this fault. This causes several thousands of buildings to collapse. And next, this also maps into the fatalities. So we see a very similar pattern. So it really is this example of this fault in the north, because it's so close to Almaty, it would be a really dramatic event if it were to happen. And next, for my conclusions, so we've created high-resolution digital elevation models and use these to identify fault splays in Almaty. And this is important to do because, as we've seen, even if the earthquakes that were occur on these were to be much smaller than large events in the high mountains, they can be a lot more damaging because they're so close to the city. Thank you very much.
Thank you, Ruth. Thank you very much. We can move to the presentation by Pierre Lacan and Christos Papaioannou. Please get ready.
Hi. Do you hear me?
Yes.
Okay. Good morning, everybody, and let's go back to Mexico, where I will talk you about paleoseismology and seismic hazard assessment of crustal faults in central Mexico and consequences for megacity within the area. This work is supported by UNAM Mexican funding and the EOLIN project. Next, please. In Mexico, most of the seismicity of the last century is localized on the Pacific subduction zone, where the majority of studies related to seismicity and its consequences have been concentrated. However, some crustal earthquakes have occurred in the Mexican volcanic arc. Next, please, in the red rectangle. During the last century, there have been only 2 destructive crustal earthquakes in this area, but they made more than 2,000 victims, mainly because more than 50% of the Mexican population live within the Trans-Mexican volcanic belt in megacities such as Mexico City or Guadalajara. Yes, perfect. If we focus on the historical seismicity of the last 500 years, we can see that several earthquakes of magnitude between 5.9 and 7.6 have occurred. Consequences of such an earthquake nowadays would be a disaster considering the growing population. However, little information was available about fault source for this earthquake, and there are still little considered in the seismic hazard assessment. Next, please. So in order to extend the seismic record of prehistorical time, we performed paleoseismic study along different fault systems of the Trans-Mexican volcanic belt. And now, next, please. I will focus here on the Acambe Graben, epicentral area of the 1912 Acambe earthquake, located at only 70 kilometers from Mexico City and its 23 million inhabitants. Next, please. The Acambe Graben is formed by 3 main fault systems. 2 of them bound the graben, while the third is located within the graben. The instrumental seismicity is moderate, except for these 2 events of magnitude 7 and 5.3 that occurred during the last century. Next. Paleoseismic study during the last 10 years led to the identification of 37 prehistoric seismic events that we have been able to date and characterize. We now have a relatively good set of data that we can use for the evaluation of seismic hazard. Next. So the integration of this data in probabilistic model is part of the objective of the PhD thesis of Rodrigo Leon. Rodrigo is studying the Coulomb stress transfer based on different rupture scenarios estimated from paleoseismic observation. And in parallel is interpreting paleoseismic data in FISH program in order to estimate the different parameters to constrain the seismic hazard related to these faults. In the future, we would like to try different models, Sheriff or other like this, to evaluate the possibility with the data we have for now with the different model. Next, please. Another student, John Diaz, with his supervisor, Victor Cruz, are working on the deterministic modeling of an event that could occur in the Acambe Graben and its effect in Mexico City by considering the site effect. In the modeling, we can see how the horizontal speed increase when reaching the Mexico City basin due to site effect. They work on different scenarios, mainly constrained by the paleoseismic data available. And the objective at the end will be to propose a probabilistic model based on the different deterministic scenarios. Next, please. Obviously, this work is a result of great collaboration with a lot of incredible students and researchers from Mexico, Europe, New Zealand. Without whom nothing would have been possible. There is a lot of work to do.
Sorry, Pierre, you have 1 minute.
Yes, I finish. We're open to new collaboration. Next. Thank you very much.
Thank you, Pierre. Thank you for being perfectly on time. You saved 1 minute. Thank you very much. So we can move to next to Christos Papaio now. Please, Georgios Diligiannakis, be ready. You are the next one.
Good evening to everybody. When I decided to participate in this webinar, I attempted to give you the experience gained from Greece using both historical information in order to parameterize active faults in the region in order to assess the seismic hazard. Next slide, please. This slide, the pictures in these slides give a view of the active tectonics in the broader region of Greece, the Aegean region. On the left side and on the right side is the main morphotectonic features of the region. The region which is under study for the in the current presentation is denoted by the black rectangle in the left part of the slide. Next slide, please. In Greece, as I told you, we have plenty of information since the 6th century BC for the damage due to earthquakes. There are written documents, and we made a huge effort to collect and elaborate this information. This was mainly done by Professor Papazachos and Papazachos, his wife. And then we, by the elaboration of this data, we defined the rupture zones of the big earthquakes in Greece, and this is from a present publication in Tectophysics 1999 by Papazachos and his colleagues. And you see the various rupture zones of earthquakes in Greece. You may denote at the southern part of the area 2 great ellipses, one in the southeastern part and one in the southwestern part. These ellipses are associated with the nucleation of historical magnitude 8+ earthquakes with large tsunamis in the region. Next slide, please. Why rupture zones, not single faults? The answer is in this slide, and that is on the left side, on the left picture, you can see the red line which represent the location of the Aegean Fault in Korinthiakos Gulf, and very active region in Greece, the most with the highest extension rate in the whole Europe. And if you can see in the lower part, you may see a representation by Bernard et al. 2006 of the faults mapped in the region. In that, these are the faults in the southern part, and you can see that the geologists marked several faults. But all these faults, if you notice at the lower part of this sketch, are associated with one fault, that is the Aegean fault, which is very active during the geological time, and the numerous activation of this fault resulted in several ruptures on the ground. So these were mapped as independent faults, but all these particular faults are linked to the main fault, which is dipping to the north. Excuse me, to the northeast. So this is the reason why we apply the not a single fault parameter, but a system of faults which belong to a rupture zone. Next slide, please. So for speaking about the region, we have two clusters of rupture zones. One is in the right part. That is a unique one we have, but it is just only one rupture. We didn't have information to determine seismicity parameters, but we have plenty of them for the fault which is dominated in the western part of the island, and you can see multiple rupture zones which are related to which the length of the ellipsis is associated with the fault, with the magnitude of the causative earthquake. Next
Sorry,
slide.
Christos, you have 1 minute.
Only? Okay.
1 minute.
Okay, next one. Next one. This region, we had the strongest records of strong motion in Greece. Next slide, please. You can see the historical information for the last 5 centuries. Next slide, please. The location of the epicenters, which are associated within the rupture zone of Kefalonia. Next slide, please. Macroseismic maps. Next slide, please. And this is the seismotectonic model used for the seismic hazard analysis using the FRISC 88 code of Robin Maguire. Next slide. The map of the distribution of the maximum intensities on the island. Next slide, please. And you can see the distribution of the maximum of the intensities for the 2 main cities on the island, Lixourion and Argostoli. And the last one slide, just compare the values which are for military periods of 100, 200, and 500 years military period on the 3 columns at the left, which are the results of the application of the FRISC 88M code, and on the respective columns of 100, 200, 500 years for military period, the expected macroseismic intensities seems that they are almost identical. So this supports that the seismicity rate parameters for this fault was calculated with acceptance errors and resulted in reliable hazard assessment based on macroseismic intensities. And the reason for the macroseismic intensities was that because we have intensities as these were the historical information. Thank you very much.
Thank you, Christos. Thank you very much. I'm inviting Georgios for the next talk.